So hi everyone, I'm Zachary Scofield. I'm a graduate student at ASIAA University, and today I'll be talking about the most distant strong lensing cluster, XLSSC 122 at a redshift of 1.98. So as has been mentioned multiple times, it's believed that the universe formed hierarchically, with smaller structures forming first and larger structures forming later. And here I have another simulation you've seen multiple times, the Millennium simulation, with 3 snapshots, redshift 5.7, 1.4, and the present day. And XLSSC 122, which I'll call XLSSC from now on, lies at 1.98 between these two snapshots at 3.3 billion years after the Big Bang. And I like to use the oxymoron to describe it, the early-late stage of hierarchical structure formation. And this is the HST image of XLSSC in the top right corner. So what makes this redshift special? First of all, among galaxy clusters from the SPT, ACT less than or equal to DR5, and Planck surveys, XLSSC is the most distant, and it's also the most distant cluster to be analyzed yet with strong lensing. And therefore, it probes a largely unexplored cluster regime in a higher detail because of strong lensing's power, I guess. There are other ways to look at clusters other than with lensing, and strong lensing in particular. You can look at the gas density of the cluster using X-ray emission, with this being XMM X-ray data from MANS 2018. You can also look at pressure within the ICM with the Sunyaev-Zeldovich effect, or SZ effect, which traces ICM pressure. You can look at turbulence as well with radio, and this is from a large-scale meerkat observation. And finally, you can also look at clusters with weak lensing, which you've heard about, not just strong lensing. And this is the first weak lensing analysis of this cluster from Jinyeop Kim this year, using HST observational data. And I'm sure you've heard about lensing multiple times, but I spent a lot of time on this visualization, so you have to listen to it again. So imagine that we have a very lonely galaxy at redshift 4 in the universe, and there's nothing else. Except this time we put a galaxy cluster in front of it at a redshift of 2, and in the absence of strong lensing, the galaxy would just be completely hidden by the ICL and BCG light, and we wouldn't be able to see it, we would never know it was there. But in reality, the background galaxy actually becomes multiple images of that same source because of the gravitational potential of the lens and how light deflects through that gravitational potential. And using these multiple positions of the same image, or of the same galaxy, we can provide constraints on the projected mass distribution of the cluster, especially around the cluster core. Weak lensing, which you've also heard about, is similar light deflection, except it's at the edges of the cluster, so where the distortion is less significant. It's characterized by convergence and shear. And this time, let's say that that galaxy has a lot of friends at redshift 4. There are a lot in this field. And we put the same cluster in front, and without lensing, simply a lot of those galaxies would be covered by the light of the cluster. And if we look at just a small region of the cluster field, these galaxies, if we average the shear in that small region, we would find that the average shear is around 0, usually, unless we have some extenuating circumstances. But whenever we introduce lensing, the average shear in that same region would become much larger. This is just an arbitrary value of 0.08. And that consistent and coherent shear measurement is what allows us to constrain the projected mass distribution, especially in the edge regions of the cluster. So, like I mentioned earlier, this cluster has been observed with HST once already. There are some problems with the lensing analysis, though. First of all, there are no multiple images in the HST data, so there are no strong lensing constraints. The background source density is 100 arcminute, or galaxies per arcminute squared, which, as someone who uses JWST, I call that low. But if you do ground-based observation, that's very high still. And the lensing efficiency weighted shear signal for this field, because it's in visible observation, and there is some infrared through HST, but it's pretty shallow. The lack of high redshift sources makes the average lensing efficiency go down, so the signal from weak lensing might be weaker. However, with JWST imaging, which I call the golden age, of course, a lot of these problems are solved. First, we have new multiple images that were previously invisible in HST imaging. If you look really hard, you might see maybe a hint of them, but no one saw them before. The source density increases by about a factor of 4 to around 400 galaxies per arc minute squared. And the near-infrared observing of the JWST and deep observations reveal a lot of high redshift galaxies, and that increases the lensing efficiency and thus increases the weak lensing signal-to-noise ratio. And interestingly, we also see very distinct evidence of extended asymmetric ICL. And if you're interested in the ICL analysis of this cluster, you should talk to Fengjin Zhu. And if I were to put it into one sentence, I would say JWST ASIAA has unlocked detailed views of cluster assembly, and I'm not paid by JWST, but let me slow down. And to look at the data more closely, we have 4 filters, F090, 200, 277, and 356. The limiting magnitudes are around 29.1 to 30.1, depending on the wavelength of the filter and the exposure time. And this data is currently unmasked, but we'll release our mosaics publicly soon through our data reduction once the first strong lensing paper is published. And that paper is Kyle Finner et al. 2025. Now for multiple images for XLSSC, sometimes with other clusters such as Able S1063, which you heard about yesterday, the multiple images are pretty obvious. You can just look at them and see, oh, they have similar colors and similar morphology, so those are definitely multiple images. But with XLSSC, we just have these strong lensing arcs that we can't really tell exactly what the multiple images might be. So we have to follow a different process for determining our multiple image selection. In our case, we looked at these arcs that show this tangential kind of orientation around the cluster, and we treated those as kind of our initial guesses for multiple images in this cluster field. And then we did an iterative process to refine. We would predict multiple image positions from this model, and then if that gave good results, we would choose that as one of our multiple images. And these are the final resulting images. There are 4 multiple image systems with 12 total images, and the redshifts of these background images range from about 2.9 to 4.5. And this is the denoised image. So you heard about that from a poster flash talk earlier from Hyo-Sung Park. So if you're interested about that, please talk to him. And so from these multiple images, we can create a strong lensing model. It is comprised of a larger scale profile for the cluster potential, as well as smaller profiles or mass profiles for the cluster members in the central region. And then using this mass model, we can estimate the mass and concentration of the cluster. And what we find is a mass of 2.6 plus minus 1.1 times 10 to the 14, which is consistent with other mass estimates for this cluster. But the interesting thing is that we find a concentration of 6.3 plus or minus 0.5. And this high concentration, of course, there could be projection effects, and it's an emerging cluster, so there may be higher concentration from that. But if it's just an aspect of this cluster, it could also point to early mass assembly, which would be interesting because if you look at this plot on the bottom here, there's concentration versus mass for redshift 2. Most MC relations predict concentration much lower than this value at this redshift, and so that could be indicating some sort of tension with our currently chosen MC relations in lambda CDM. But it needs support from weak lensing, and that's my main area of expertise. So for the source selection for weak lensing, we used a color magnitude selection to select background sources. The top right plot here shows the blue sources that we selected, and then these red sources are the red sequence as well as kind of the blue cloud. These are spectroscopically confirmed member galaxies. And we compared this source selection to a reference field, Jade's Good South in this case. And in doing so, we ensure that there's no excess in the brighter galaxies that could suggest cluster member contamination in our sample. And then you just heard about the Mars mass modeling technique. So this is another use of it. It's free-form, and I won't go into too much depth about it. You can talk to Sang-Jun Cha if you want more information. But this is the mass map for this cluster. And if I do a nice fade into the contours, this is after bootstrapping, and we get a mass peak that's 8 sigma significance, and it's spatially consistent with the BCG, which is interesting because this is a very different mass distribution than we see with HST. it shows a completely different orientation angle and elongation direction compared to ours. And that could be due to source density differences or lensing efficiency. But from weak lensing, we estimate the mass to be consistent with the strong lensing result, and we also find the same concentration. So we find that weak lensing and strong lensing agree, but making any assumptions about the universe from one high redshift cluster is dangerous, so we're preparing a proposal to do more studies of this kind with other high redshift clusters. And this is the tangential shear fit. We measure the tangential shear like I showed earlier and find the mass from that, from fitting an NFW profile. And so one reason why we think our elongation from weak lensing is more correct is because when we look at this cluster through different wavelengths, right, we see this is weak lensing, this is X-ray from Chandra, and it has a similar elongation. Same with radio, although the radio is not that significant of a detection, so tentative about that result. The SC offset doesn't show the same elongation, but that's expected. And BCG plus ICL is really in good agreement with the weak lensing analysis. So this kind of hints at a potential merger axis for this cluster. And this SC offset that I mentioned, this has been covered in Arawick 2024, but this SC peak offset is kind of strong evidence of a major recent merger as well. And we see this offset from both the X-ray peak offset and the weak lensing offset, as well as the BCG, of course. And so in conclusion, I think JWST's depth and resolution reveals high redshift sources, and that allows for precision, strong lensing, and weak lensing. A high concentration of this redshift could potentially point to early cluster assembly, but it would need support from a larger sample of clusters. And the elongation of weak lensing ICL and X-ray in the northeast-southwest direction, as well as the SC pressure peak offset, points to a recent merger. And as a take-home message, I would say JWST turns structure formation from at redshift 2 from hints into measurements, and XLSSC is the pilot study with more high redshift clusters to come. Thank you. Thank you.
Okay. Questions?
So about the concentration, so longitudinal, you said that that value is much larger than longitudinal predictions, but each cluster has scatter. So thinking about that scatter, how many sigmas is that away from longitudinal?
How many? For the strong lensing or the weak lensing?
Both. I think both are similar, right?
Well, here, this is the kind of uncertainty for concentration estimates. And I mean, it's pretty significantly, I don't know the exact kind of sigma ratio, how significant it is above these other MC relations, but it shows a significant difference. Yeah.
What is the orange line?
The orange line is from Prada 2012, and that comes from kind of their different method for doing the MC relation. It's based on circular velocity rather than an NFW fit, and they also used a different kind of radial binning scheme. But it's been found in a 2013 paper that Prada 2012 becomes consistent with Duffy 2008 if they use kind of the same radial range.
I see. Thank you.
Yeah, thank you.
Okay, we have time for one more question.
Thank you for the next call. I have a problem about the redshift. How do you do the model fit for that? And if we get more source spectropy, it will help for us to estimate this redshift.
Estimate the what did you say at the end?
Estimate the redshift range for
the background sources?
Yes.
Yeah, so it would be nice to have spectroscopy for those multiple images. I think that's one of the main problems with trying to do strong lensing at this redshift is we didn't have good spectroscopic redshifts, or the photometric redshifts were also uncertain because of this few number of filters, and of course there's no observation in HST of those same features. So yeah, if we had spectroscopic data, I think we would have a much better idea about the multiple images format, I guess. Thank you.
Okay, let's thank all the speakers of the session. We're